Okay, so we're now at question 3 of the mock. So, okay, so we've got some text before we even start any of the question parts, so they could be relevant to any of the question parts that follow. So refrigerants are substances used to cool refrigerators and freezers. Until recently, many of the compounds used as refrigerants were chlorofluorocarbons, CFCs, but these are now known to form chlorine radicals. CFCs have been phased out in many countries by international agreement. And then the first question we've got is write 2 equations to show how chlorine radicals, so clearly we must be using a chlorine radical in our equation, right? That's got to be there. And then how they react with ozone molecules. So chlorine radicals, we're going to identify them like that. And then ozone molecules, you need to remember what an ozone molecule is, otherwise you can't do the question. Has the formula O3. So straight away, if we appreciate what that's saying, if we remember that a chlorine radical is a Cl with that unpaired electron, that's what makes it a radical, and ozone is O3, then we have got the start of our equation, right? And we're told, actually it doesn't tell us what it's being broken down into, but one thing to remember is that ozone is broken down into oxygen. Okay, so we're breaking it down into oxygen, and if this is a propagation step, these are propagation steps, and the fact it has a 1 and a 2 sort of tells us, I mean, it doesn't tell us explicitly, but it tells us these are propagation steps. Then in a propagation step, you always have a radical and a molecule on both sides of the equation. So our radical is our chlorate ion, it's our chlorate free radical. So whatever free radical is on the right of the first equation must be on the left of the second equation. So this is like this is a consequence of the first equation. We are reacting with ozone again, and we are reforming our chlorine radical. So that's why we get a chain reaction. So the chlorine radical is reformed, and so can go and destroy more ozone molecules, which is why only a very small number of chlorine radicals can have a massive impact. And we've got to balance our oxygens, so 2O2. And not that you have to do this, but one way of sort of checking, or one way of sort of thinking about this is when you have 2 equations like this, you can add them together. So this is just to show you something that's important and useful. So if I now write every species on the left hand side, because that's what I'm doing, I'm adding them together. So we've got our chlorate, and then our chlorine free radical, and then 2 ozone molecules going to our let's do it in the same order. Chlorate plus chlorine plus 3 O2 molecules. And if this was maths, you'd be able to cancel things that are both on the same side. So what we get is an overall equation, which is the decomposition of ozone into oxygen. And the fact that the chlorine free radical was reformed means that it is acting as a catalyst. You didn't need to know that to answer this question, but I think if we're using these questions as a way of reminding us about different parts of the course. So, you can just memorize those 2 equations that we've written, 1 and 2, and that's fine, because it is, if they're going to ask you about chlorine radicals and ozone molecules, it's going to be those 2 equations. But obviously, if you can understand better what's going on or some of the implications surrounding it, then the better. But yeah, just to remind you, these were propagation step, or is the propagation step in free radical reactions. Okay, B. So chloropentafluoroethane is a CFC that is used as a refrigerant. Draw its displayed formula. So displayed means you have to show every single bond. So interestingly, there are no numbers in this name. So what that prompts me to do is look at the end first. So the fact it's eth means that there are only 2 carbons, and it's ethane, so it's a single bond certainly between them. And then I'm going to look at chloro. So it just says chloro, so there can only be 1 chlorine. And then it says pentafluoro. So we've got fluorine and we've got penta, so we've got 5 of them. 2, 3, 4, 5. Okay. Not much more to say about that really, but it's about taking care when you're looking at the names and try and just do it systematically, trying to have a strategy, a sort of a system for approaching it. Just to say, while we're talking about, or while we've got displayed formulae here, if there was a carboxylic acid or if there was an alcohol, you would need to make sure that you drew every bond. So that is correct, whereas this is not correct. This is correct if we were being asked to do a displayed formula of a carboxylic acid, and this is incorrect when we're talking about displayed formulae. Right, so take care. All right. Okay, so 1,1,1 trifluoroethane. So the 1,1,1. So with trifluoro means there are 3 fluorines. We can see that in the molecular formula. In fact, they've given us a structural formula. Sorry, not a molecular formula. So we can very clearly see that there are 3 fluorines bonded onto 1 carbon. It's one of the molecules that has been used as a refrigerant in place of CFCs. Explain why 1,1,1 trifluoroethane does not lead to the depletion of ozone in the upper atmosphere. So this whole question, by the way, is the halogenoalkanes, or what we've been doing so far certainly is halogenoalkanes. And if you think about the halogenoalkanes you've ever done mechanisms for, you will have never done a mechanism involving fluorine. So the halogenoalkanes you've ever drawn reaction mechanism for have never been fluoroalkanes at all. And there is a very good reason for that, and it's also the same reason behind the answer to this question, is that the carbon-fluorine bond, or bonds, is too strong. In fact, let's make it bonds. So they don't break. So in the case of forming these radicals, this is it's about UV light, which is essentially a transfer of energy. And UV light provides enough energy to break carbon-chlorine bonds, to break carbon-bromine bonds, but it doesn't provide enough energy to break carbon-fluorine bonds, though they're too strong. So that would be enough, but I'm going to put and do not break for you. Alternatively, another way of approaching this, and so there are no radicals formed, another way of approaching this is that we could just simply say it does not contain chlorine. Therefore doesn't release chlorine radicals. But I think remembering that the carbon-fluorine bond is too strong is useful also for other potential questions surrounding halogenoalkanes where you might have fluorine, and there's nothing to say they couldn't ask a question having 2 halogenoalkanes and say, why does one react with your aqueous sodium hydroxide and the other not. And similarly, that question earlier, question 1, where it was comparing a bromo alkane and a chloroalkane, and he talked about the bond strength, the difference in bond strength, that the carbon-bromine bond was weaker. Similarly, there's nothing to stop it being fluorine. So you're making a comparison there. Okay. All right, so one of the steps in the synthesis of 1,1,1-trifluoroethane is the reaction of 1,1-difluoroethane with fluorine in a free radical substitution reaction. So this is now technically would feature in the alkane. So even though we've got halogenoalkanes here, free radical substitution reactions really first appeared in the alkane topic. Write 2 equations to represent the propagation steps, and where we're converting our 1,1-difluoroethane into 1,1,1-trifluoroethane. So obviously we are reacting our difluoroethane molecule, and we must be reacting it with a fluorine free radical. So it would take quite a lot of effort to do this reaction, actually. So it's quite interesting they've chosen to do this, given you've probably never seen a fluorine radical in a question before, but the principles are still the same. And what you've got to try and get a sort of a pattern into, if you want a system for approaching these. So you always have a radical and a molecule on both sides of the equation when it's propagation steps. And on the first propagation step, if it's a standard, alkane free radical, it's not the ozone one. If it's something with hydrogen in it, you always get whatever the free radical was now bonded to hydrogen. So hydrogen fluoride here. So that means what we've done is we've stripped off or taken off the hydrogen that was in our original, our starting molecule. So that is now the free radical. Whoops. Now, the hydrogen that got stripped off is off the first carbon, so the free radical should really be on that first carbon. They will, in the mark scheme, they say credit the dot anywhere on the radical, but again, there's always a chance that changes at some point, and we want to be correct, don't we? So the free radical is on the carbon with only 2 fluorines. So then on our second propagation step, we always have the free radical that we formed at the end of the first equation. And then we always react it with the halogen molecule, but the halogen that we're interested in. So fluorine, because that's what we're adding to our, or substituting in our original molecule. And that then gives us the product, the thing that we want. And then we always reform our original free radical, just like we did before. So if you think about what clues they're giving you, or clues, but things they're telling you, is that when they're saying conversion of, that has got to be on the left-hand side of the first step. And that, our product, has to be on the right-hand side of the second step. And then whatever radical you're adding, whatever thing you're adding, which is fluorine, that has got to be the radical on the left-hand side of the first step and the radical on the right-hand side of the second step. So, and then it's also got to be the halogen that you are adding in the second step. Let's do what I did on the previous earlier on, where I added them, because I just want to show you that this is a consistent thing here. So I'm going to add the 2 equations together. So CHF2 CH3 plus F dot plus, and then CF2 CH3 plus F2. So that's everything on the right-hand side of those 2 equations. 2CH3 plus HF CF3. oops, sorry, CF3 plus F. And let's look at the things we have on both sides. So we have that radical on both sides, and we have that radical on both sides. So when we look at the overall equation, so there we go, the overall reaction equation. And just to remind ourselves again, that has been reformed. Catalyst. Okay. But of course, I'm just adding stuff around to try and explain more than just give the answers. Yeah. Okay. So now we have a calculation question. So a refrigerator contains 1.41 kilograms of, and then we've got our trifluoroethane. So calculate the number of molecules in the refrigerator, give your answer to an appropriate number of significant figures. And then we've got Avogadro's constant. Okay, so let's go through this carefully. So first thing is that's in kilograms. So, you know, I would think about doing this as and when you're reading it. You know that you're going to have to do a calculation, and you know that chemistry deals in grams. So we should be converting that into grams, and there are 1,000 grams in a kilogram. So 1410 grams. Okay. The other thing we should do is we're going to be having to work out, we've got Avogadro's constant, so that's per mole, so we're going to work out moles. So we've got a mass, so we should also work out an MR. So we have 2 carbons, and we have 3 fluorines, and we have 3 hydrogens, and that equals 84.0. But of course, you might have to look it up, you know, look each of those values up on your periodic table. So let's work out moles, right? So our number of moles equals, and then it's mass over MR, but mass in grams. Okay. And the units are incidentally of MR because it's quite useful to know a grams per mole. And that's how we're going to get moles as our final unit, because the grams will cancel out and we'll have 1 over moles, so moles. So we've got a mass of 1410 divided by RMR, and then we can do equals on that. So 16.79 moles. I guess actually, before I carry on, I guess the other thing I should have done is look at the significant figures in advance. I mean, what I would say is always keep everything in your calculator until the very end. So I might write 16.79, but I keep the actual number. Let's just do that, 1410 divided by 84.0. Okay, so I've got 16.785714. Right, I'm going to keep that in my calculator, but I'm going to write on my paper 16.79. So sorry, let's just look at, we've got that, which is 3SF, 3 significant figures, and we have got that, which is 4 significant figures. So that's the data that we're putting in. Our MRs, 3 significant figures, but we're looking at the figures we're starting with. You always, the correct number of significant figures, or the appropriate number, will always be the number of significant figures that was the smallest number that was used in the calculation. All right, so we've used 3 significant figures, and we're going to use 4 significant figures, but 3 is the smallest, so that's what our final answer is going to be. Okay, now we want the number of molecules. So the number of molecules is going to be the number of moles. Sorry, going wrong here. Number of molecules is going to be the number of moles, which is 16.79, but obviously I've left the number in my calculator, times the number of molecules in a mole, which is Avogadro's constant. Put that in brackets, okay. Which equals, so I put in my Avogadro's constant, 6.022 times 10 to the 23. So I've got 1.010835714 times 10 to the 25, but I've got to do it to the appropriate number of significant figures. And there's my answer. And there are no units. It's just a number, because if you think about the units we were using, we had moles times, and then if you look at Avogadro's constant, it's per mole. So when you multiply those together, there are no units. It's just a number. Okay. Any questions about that, please ask. And then final part of this question, there are growing concerns about the use of 1,1,1-trifluoroethane as a refrigerant, as it is a greenhouse gas that absorbs some of the Earth's infrared radiation. Give one reason, so there's obviously more than one that we could perhaps give, why bonds in molecules such as carbon dioxide and our trifluoroethane absorb infrared radiation. And if you think about, you know that the atmosphere is mostly nitrogen, then a significant, like a fifth of it, over a fifth of it is oxygen, and then we get lots of, much smaller amounts. And nitrogen and oxygen are never talked about as being greenhouse gases, because they're not greenhouse gases. And yet all the other things that are talked about greenhouse gases are, methane, carbon dioxide, here these CFCs or whatever, and it's basically compounds. And the reason is that in all of these, in carbon dioxide, in our trifluoroethane here, they contain polar bonds. It's the fact that they're polar. The reason that makes a difference is because the consequence of that is that they vibrate. This is they're absorbing the energy, or they stretch, or they bend. So if you said bonds vibrate, or bonds stretch, or bonds bend, or contain polar bonds, any of those 4 comment statements, then you would get the mark. But the vibration, the stretching, the bending, how you recognize whether something is going to vibrate, bend, stretch, whether it is going to absorb infrared radiation, is essentially if it contains polar bonds. So any questions about any of those questions, let me know.